Okay, so this is Unit 4 of the series of video tutorials on structuring code as part of the Level 2 Coding and Data Analysis topic. So in this video I'm going to introduce you to exactly what a module is, how Python works when it imports modules, what's really going on there, and then in particular talk about how you can write your own code in the form of modules, some of the things you need to pay attention to, and this is going to be really important because the work you go and do for your vitals assignments for the level 2 coding topic, you're going to be submitting code as a module into the autograders. Okay, so let's go and get started then. So the first thing I want to go and talk about in this first part then is what is a Python module and what happens when you import one. So you're familiar, I hope, with the idea from your level 1 coding course that because Python doesn't have that many functions built into it, a lot of the functions and functionality we use in Python we get by importing modules and importing the functions into our code as we need them. So a module is very simply in Python is just a file that contains Python code. That normally means function definitions and sometimes variables, and in object-oriented programming it can also mean Python classes, but that's beyond the scope of this course. And they're made available to a program that has imported the module. So the reason we have modules, the reason we use them, well, it helps us to organize our code together. So grouping together functions that are related and breaking a large program out into smaller chunks that makes it easier to read and easier to understand. It allows us to reuse our code, which is absolutely critical. So rather than having to rewrite every single possible function you need every time you write a new program, we can reuse code that we've written before, or indeed it allows us to reuse code that somebody else has written, and this allows us access to additional features, and in particular where somebody has gone and already invented the wheel, we don't need to go and reinvent the wheel badly multiple times. We can just use what somebody else has done, and this is what we get when we're importing modules in. But the important thing is that sometimes you want to go and write your own collection of modules, write your own modules. So in other words, you're the expert that's inventing the wheel, and you're inventing the wheel for somebody else to go and use. So let's go and talk about what actually happens when you do the import statement. So the actual technical details of how Python imports a module can get really quite complicated and are well beyond the scope of the course. But it's good to have at least an outline, a rough idea of what is going on there. So Python takes several steps in sequence when you tell it to import a module. So the first thing it does is it checks the module, whether the module is already imported. If a module is already imported, Python won't re-import it again. It'll just give you the thing it's already imported. If the module has not already been imported, then the first thing it needs to go and do is find where the module's code file is on the disk. Once it's found a file that contains the module, or it thinks it's found a file that contains the module, it may need to go and compile the code to prepare it to run it. Then obviously it has to run the code. Again, this is, I think, something that is a little bit different from some other programming languages, and it's something that often students don't quite get. When you do import, it's actually running the code in the module. And then finally, once it's run the code, it has to store that module code somewhere, the results of running it, so it can access it again as you need it inside the program. So let's look at those steps in turn. So first of all, checking that the code is already imported. So Python maintains a record of which modules have already been imported. And the first thing it does when it comes across an import statement is it checks to see whether that module is in its record of things that's already imported. And it's actually possible for us to go and look at what Python thinks it has imported, or what it knows it has imported, because we can get at it from one of the things that's in the sys module. So the sys module contains a whole bunch of stuff which is useful for how the Python itself is running. So if we do an import sys and then ask it for sys.modules, what we get back, and this has gone off the end of the screen, is actually a dictionary where the keys are the names of the various modules, and then the values are the result of having imported the module. So this is what happened when I ran it on my Jupyter notebook as I was writing this set of notes, and it's a huge number of modules that are imported, but that's because the Jupyter environment is actually written in Python, and so obviously it's imported a whole bunch of different code and so on in order for it to exist as an environment at all. So it's not that surprising that when you ask Python what modules it's imported, you get a massive long list to start with. But even if you do it on a very bare, just a standard Python prompt with nothing fancy going on, it's still actually quite a few modules are automatically loaded for you. So that's the first step. Let's assume then that the module is not already imported. It's now got to go and figure out where to find the module. And in order to go and do that, it's going to look for a Python file with the same name as the module we're trying to import, and it's got to go and look in a series of different places on your computer's disk. And the places it looks is stored in sys.path. So again, having imported sys, you can get access to sys.path, and on my laptop this is what it came back with. So it's just a list of strings. Each string represents somewhere on the disk where it should go looking to see if the Python module exists there. And it'll depend a bit exactly on how your Python is set up as to what things are in there. So what Python does is it looks at each of these directories on the disk in turn, and it tries to see if there is a file in there with the right name. So if you're trying to import my_code, Python will be looking for a file called my_code.py in each of those directories in turn. As soon as it finds a file, it will then move on to try and import that particular one. One of the things to notice is in that list of directories there was an empty string, and that is being used as a shortcut to mean the current directory, the current thing placed in the hard drive where Python thinks it's working from. That's usually the same place as the program or the notebook that you're running. And that's useful because it means that any file you put next to that thing you're running or that notebook you're running can potentially be used as a Python module. Sys.path is just a list, so you can append and insert and remove directories from it to change where Python is looking for code. So for example, in my laptop, the very first entry is a path that points to where I keep some code I work on and route it regularly. So I've created a custom Python path like that. So you can manipulate where Python looks, but most of the time the defaults are what you want to do. So I wouldn't recommend messing with sys.path unless you really know what it is you're doing. Okay, so if Python has located the module file, it's found it in one of the folders. So then the next step is it has to compile the code. Now this gets maybe a little confusing because we often describe Python as what's called an interpreted programming language, meaning that it's translated into instructions for the CPU as it goes through running the code. So in other words, it's translating to produce the exact machine code that the CPU in your computer has to execute as it runs the program. That's in contrast to what's called a compiled language, where before you run the program, the first thing you go and do is you convert the entire thing into machine code for your computer. And in a compiled language, the process of preparing that code to run on your computer and running it are two separate things. And that's why when you get a program download a program off the internet or something, you're normally downloading the compiled code, you can just run it straight away because someone's already done the process of converting it to the appropriate machine code instructions. The truth actually is a little bit more complicated. So what happens is Python is translated not into CPU instructions, but into a set of very basic instructions that are do kind of straightforward, simple little atoms of operations, and then those are all stored into a .pyc file, which is where Python keeps its compiled code. So if you look on your computer's hard disk in where your Python is installed, you'll probably find a whole bunch of .pyc files, and those are Python's what are called bytecode files, where it's broken these the Python script language, the text you write, it's broken it into these intermediary basic instructions. Those basic instructions are then translated into very well optimized CPU machine code instructions and then run in a sequence. So when a Python file is executed, Python first checks to see whether a PYC file already exists, and if it does, it just uses that. Otherwise, the first thing it does, it has to generate the PYC file. That's the reason why big Python programs, like for example Spider or JupyterLab, tend to be a bit slow the very first time they're run, because as they're running, they're converting all their instructions into PYC files, and then after that, Python doesn't have to do that again. It can just go away and straight run the code. So the first thing that goes on after the Python's found your module file is it converts it into a .pyc and builds up the list of the instructions. So that then means the next thing it goes and does, it actually executes the code. And as I said, this is the thing that's a bit different from how some other programming languages work. In Python, when you import the module, at the time you import it, it runs the entirety of that file. So any code that you have in a file that you're importing will get run when you do the import. And so that's one of the reasons why it's important to think carefully about what code you've got there, and to make sure that you're not assuming that things are going to be okay. You're not assuming things about the computer on which you're running the code as it's being imported. And we'll show you in a later part how to work around this effect and how to control exactly what is running and what isn't running when you do the import. The very final stage of the whole exercise is it has to store the results of running that module code. And that's where it comes back to sys.modules. After it's run the code, it takes all that executed code, all the results of running it, the functions it's defined, the variables it's created, and it all stores it in the sys.modules dictionary, so that the next time you need to work with that module is already there and loaded, and you don't have to go back through the process of re-executing it again. The side effect of this is it doesn't matter how many times you import a module, it runs once and only once, and after that it's there in sys.modules. And the only way of making it re-imported again is if you start messing with what's in sys.modules. And again, not really recommended that you go and do that, because it can really mess up your Python and cause all kinds of fun and games with it. Okay, so in the next part of this unit, I want to go and talk a little bit about writing your own code for use as a module. So, as I was just explaining, a Python module is just a file which contains Python code and has an extension .py. And as you work in bigger projects and bigger coding problems, you're going to be able to write your own modules. And more immediately, for all of the assignments, all the assessments you're doing for the vitals for level 2 coding, you're going to be submitting them as a module as a .py file of your solution. So as I said, all we have to go and do is create .py files, so plain Python code files with .py extension that contain the code. So for example here, I'm going to make use of the code we've written in Unit 2 of this strand on structuring code, which is a Fibonacci sequence calculator. And what we want to do is we're going to put it in a file called Fibonacci.py, and this is the code that goes in there. Okay, so having done that and created that file, so if I go over to Spyder, here is my Spyder, and I've just created a file called Fibonacci.py, and it's got that function in it. For a description of how that function works and what's going on, go and watch Unit 2 of the code. And in order to go and use this, I just do import Fibonacci, like so. And I can do this in a program, or I can do it in my console here, whatever works best for me. So there we imported it, and once we've imported it, we can now use that function that's defined inside it, which works straightforwardly. This is just calculating the Fibonacci series up to a term which is no bigger than 1,000, and so that's great. That works. So that, in a sense, is all we have to go and do. That's defined a Python module, and we're able to use it. If we want to look at what's inside a module, then we can use the dir function, and that will tell us what functions and variables are defined in our Fibonacci module. So if I do that, then I get an output that looks like this. And we can see at the end there is our Fibonacci n function that we were just using. And then there are a whole bunch of other things in there, all of which have names which start with double underscore. And one of the things to understand about Python is every time you see something with a double underscore, you want to be thinking, that's something a bit special to do with how Python actually works. It's a special variable or a special function that is involved in how Python's actually working underneath. So I'm going to show you what some of those are actually used for and why you might want to know about what they are. So the first question is, well, what happens if you had two module files with the same name? Well, as we said in the first part of this unit, Python is going to search sys.path, and as soon as it finds any file with the right name, it's going to try and work with that one. So any other module file with the same name that comes after that in sys.path will never get seen, it'll never get loaded. And again, this tells you need to be a bit careful with sys.path, because you could, for example, create a file called numpy.py, put it in a directory near the start of the path, and now you won't be able to go and use the numpy package because you've written a module called numpy that presumably doesn't do the same thing. So you need to be a little bit careful. What you can do is, having loaded a module, you can say, well, where's this module come from? And in order to go and do that, you can look at the __ file __ special variable. So if I just look at Fibonacci __ file __, then on my laptop, this is where it recorded. So it's the folder where I'm writing the this particular unit. When we import the module, you remember it says it gets added to sys.modules. It gets stored in sys.modules, and sys.modules is a dictionary, and the keys of the dictionary are the name of the module. So Python needs to work out what name that module is to be given. This is normally the same as the name of the file that you've loaded it from, but importantly note that's not necessarily the same as the name you're referring to the module in your code. So for example, you might import NumPy as NP. The name of the module is NumPy. The name you're referring to it by is the NP. We can see what name Python is using for a module by looking at the __name__. I'm going to say dunder. Dunder is a bit of Python speak, which means double underscore. So we say dunder name, I mean double underscore name, double underscore. So if we look at that for the Fibonacci module, so Fibonacci.dunderName, it comes back and tells us it's called Fibonacci. That's not a surprise, it's been loaded from Fibonacci.py, so that's why it's got that name. But as I said, if we import the name with an alias, the name that is returned by dunderName remains the same as it always would do. So here's the example I was talking about before. I import numpy as np and then ask what's np.dunderName, and it comes back and it tells me it's numpy. So it doesn't matter if I import modules with different aliases, Python knows it's the same module. And so there's only ever one imported once, and only one of it lives in sys.modules. And you can test whether a module exists in sys.modules. This is just the same way as you test whether a key exists within a dictionary, because that's all we're doing. Sys.modules is just a dictionary. It's a dictionary whose keys are the names of the modules, and the values are the results of importing the module. So since I've imported numpy, numpy is in sys.modules, and so it returns true. The dunderdoc special variable will contain the module's docstring. So in the debugging unit 3 videos, I was talking about docstrings and how important docstrings are for helping you keep track of what your code is doing. So as well as having a docstring for a function, a module can have a docstring as well. There's less strong conventions about the formatting of a docstring for a module, but it's still useful for it to go and describe what the overall purpose of that module is. What functions does this module contain? Where are they being used for? Maybe a link to some documentation for it. So a docstring for a module is simply the first line of the string, a string on the first line of the module. So again, we can go over to our Python code, and here I've got another version of the Fibonacci code, and I've just put a string on the first line, and that's the docstring for the whole module. That's different from the docstring for the function. This is the docstring for the module on the first line here. So if I was to do that and then print Fibonacci.dunderdoc, then it'll print out that string that I've defined at the start of the file. And that's the same thing you get if you ask Python to query or to give you the information about the Fibonacci module. So again, one of the things you can do in Jupyter Notebooks, or if you're using the Python console in Spyder, is you can type the name. In fact, I think this even works in just straight Python. You can type the name of the thing you're interested in, put a question mark after it, hit return, and it will give you a little bit of information about that, whatever that is. So in this case, it tells you it's a module. It tells you that it's been loaded in from the file it's been loaded in from, and it prints out the docstring as well. So it's kind of giving you some basic information. Of course, if the docstring was longer and more complete, then you'd have more information there. So again, if you're writing your own modules, it's a good idea to give it a nice docstring. So sometimes when we're writing our own module, we also can define our own Dunder special variables. These are only done by convention. There's no, although they've got a special double underscore, they're not really part of the innards of Python, but they're used to indicate that they're giving you what you might say is meta information about the module that you're working with. And so some of the common ones are sometimes you might specify an author, and often you specify a version, and that can be useful because you might need to go and check if you know that a particular function was only defined in a certain version of a module. You might want to check that you've got the right version of the module before you start trying to go and call a function that may or may not exist. So indeed, if you go and do this on NumPy and look for numpy.__version__, then it comes back and tells you which version of NumPy you're using. Of course, that's going to depend exactly on how recent a version of Python you're using. So it may be version 2, maybe version 2.1, I think even version 2.2, might be version 1 point something. That doesn't really matter. But it's giving you information about the module. So in this third part of the video tutorial, I'm going to talk a bit about including testing code in your module. So again, I've talked about this in the debugging series, the importance of trying to test your code as you go along, and that's especially true of a module. So as you write the functions into a module, you probably want to go and test the code you're working. So for example, in our Fibonacci module, we might want to go and check that it actually produces the right answer if you ask it to calculate the n terms correctly. It's convenient to put the test code in with the module itself, so it lives in the same place, and that means it's easy to go and make sure that as you adapt and write new functions, you're also putting in some tests to check that they're working correctly. The problem is that when a module is imported, everything is run. So if you have test code just sitting there in the module, every time you import it, it will suddenly start trying to run the test code. And if that test code takes a long time to run, or it refers to a file that might not exist on the computer where the code is running, or it might try and print things to a screen that might not exist, that is not good. So we want to be careful about making sure that our test code doesn't run if all we're doing is importing the module, but it does run when we want to run it. And the trick to doing this is to do with the special dunder name variable, the __name__ variable. So we saw in the previous part that when you import the module, Python automatically creates this variable, dunder name, and it gives it the name of the module, or whatever it thinks the module is called from as it was importing it. If you just run a Python module as a script, as a top-level program, so in Spider that means I press the play button on the toolbar, or I press F5 and it starts running the script. I'm not importing that code, I'm just running it. And so the __name_ variable won't be the name of the module because it's not being imported. So in this circumstances, that variable is set to a special value. So Python automatically says, you're running this file, let's create this __name_ variable and give it this special dunder main value. And so that becomes a way that we can test, is this code being run because we're importing it, or is it being run because we're actually running it as the main script, the main program we're running? So that enables us to write a test that checks that, and then we can put all of our code that should only run if we're running this as the top level main program could go inside that test, and otherwise if we're just importing the code, it won't run it at all. So this is how it looks. So this is our Fibonacci series, and you see down the bottom there we have that test for whether the special variable is equal to that special value that says this is running as our main script. And if I execute this code cell in Jupyter, or if I go over to the Python code, let's go to the one which has that defined like that. So if I press F5 and run this code, then you see it prints out the sequence. But if I import, this is called Fibonacci 2 to distinguish it from the other versions. Let's just import it as Fibonacci. Then you see it hasn't run the code. When I did the import, nothing happened. When I ran the code, press F5, it executes those lines where it does the calculation, but importing it doesn't do anything. But I have got the function there. Oops. Fibonacci n. If I just ask it to run it, then you see the thing does exist. It is defined. So by putting the code inside that guard clause, I'm able to make sure that it will only run when I run the code, and it won't run when I import it. And that is the correct thing to go and do when you're writing code to be used as a module. In fact, I even go so far, it's the right thing to go and do whenever you're writing a py file. So I think every .py script file you write, you should always have that guard clause in it, so that you can distinguish between things that happen when you import and things that happen when you just run it. Okay, so that was what I was just saying. So if you have a lot of code there, what a common convention is to go and do is, rather than just putting the code inside the if dunder name equals dunder main, actually what a lot of people recommend that you create an entire separate function. Traditionally this is called main. This is sort of inherited from the C programming language, but you know, it's a convention, and you put your code in there. So in this case what's going to happen is that when I run this code, it's going to go and call the main function, and that's going to do whatever else it needs to go and do. But if I just import it, then it's going to just go and define two functions for me. So again, we can go over to the spider, and Fibonacci 3 has that defined like that. So if I run that code, it runs the main function. Let's just demonstrate it's doing that by inside main. There we go. So you see it's printed out that it's inside main when I've run it. If I just import Fibonacci 3, oops. Let's just import it as Fibonacci. Nothing's happened, but because I've imported it, I do have a main function there, and if I run the main function, it does the same thing as what I would have done had I run the code. So that's just showing that, again, this guard clause is stopping it from running the main function when I just do the import, and I have to explicitly tell it I want to run the main function after I've imported it. Or alternatively, if I run this as a top level program, as the main program I'm running, it's going to run anyway, because when I run it as the main program, that special variable has the correct value that if statement triggers. So that's the correct way to go and set up a module. For the assignments we're writing here, you won't necessarily need to have a main function. In fact, in some cases, probably also only want to see one function. So if you have an extra main function, it may not pass the autograder. But the important thing you should do is you always have that if statement in your code, and that's an important thing to do. So as I said, we want to see that if statement for everything you're submitting for the level 2 coding. Okay, so for the final part of this unit on modules, I just want to talk a little bit about what happens when we go beyond the simple Python module and talk about Python packages. So as you write more and more code, keeping things in single modules doesn't quite cut it. We need to have a way of collecting together related modules. And this is done in Python by using the Python package. And actually you've been using Python packages already, so things like NumPy and Matplotlib are examples of Python packages. And we can see what happens if we look at the dunder file special variable that you've got in NumPy. So remember the dunder file special variable we looked at in the previous part, that gives you the file name of where the module is. So what happens when we do that with NumPy and we ask it for its file, then you see what it's telling us is it's actually inside a file that's called __init__.py, and that file lives inside a directory, a folder called NumPy. Well, remember again, every time we see an __, you want to be thinking, that's probably something to do with the internals of Python. And if Python has a directory which contains an __init__.py file, then Python will understand that that directory is a Python package whose name is given by that by that directory name. If you look on the disk inside that directory, then you'll see that there are several module files, so several .py files in there. So inside NumPy, for example, I think there's normally a module called ctypes.py, and there will also be folders which themselves contain _init.py files, __init, so for an example would be the FFT directory, which contains a fast Fourier transform package. So there are packages and sub-packages, and you can have sub-packages and so on. And you'll see this and you'll be using these. So if you read, say, the NumPy documentation, it'll maybe tell you that you can get something is in numpy.fft. So you do from numpy.fft import something or other. That translates to Python. It sees the dot in the name of the module and says, the first part is the package, and the next part is either the module or the sub-package I need to load from. So when you're actually importing the NumPy package, what it's actually doing is running all the code that's in the __init__.py file. And that's the thing it's really importing, and that's the thing whose results it puts in sys.modules. So if that dunder init file itself starts importing a bunch of things, then those become things that are available within the package. So for example, in this case, the dunder init file in NumPy will import ctypes and import FFT, and then that means that becomes available to your program as numpy.ctypes and numpy.fft. So it's able to build together and reference a whole collection of different modules under a root, under a common root, which is the package. And then the submodules of the package potentially also have their own names within sys.modules. It depends on exactly how you've imported them. So, and often in many cases there's some trickery going on, and NumPy is a good example of this, that actually NumPy won't import all of the submodules until you try using them. So if you just import NumPy, then you won't find numpy.fft is in sys.modules, but as soon as you try referring to numpy.fft, then it exists within sys.modules. So there can be a little bit of fun things like that going on. But the main thing to take away from this is just the appreciation that just as a Python module is just a simple file that contains a Python code, a Python package is a collection of modules and is just a directory that contains Python files, or with a .py extension.